Thank you very much for the invitation. I'm very, very pleased to be here in Winterthur in Switzerland. I'm Loïc Domenier, and I will talk today about the optimization that Zephyr is doing for you. I don't know who is a bare metal developer doing exactly. Okay, all right. And the people using Zephyr again. Okay. So we have seen in the first talk many good examples what we can do with Zephyr, kind of Lego building blocks that I can use to build my embedded product. And the nice things about Zephyr, it's abstracted away and we can easily port from one board to the next, or more easily if we do it manually. And if you are coming from bare metal, immediately you have some bells ringing. Oh, what does that mean in terms of code size and code speed? Because abstraction means that you have made perhaps indirections, mean that you have a performance impact penalty. And that's exactly what I want to discuss with you today to show you on a very simple example, the Blinky one, the kind of optimization techniques Zephyr is using so that you have the advantage of the abstraction that you can move across board without sacrificing, without that it costs too much in terms of memory and speed. Years of experience in software engineering. First, working in industry like telecom, air traffic control, medical, automotive. But now, since that 2018, I'm working at Doulos, which is a training company specialized in hardware design and verification, but also in embedded. We are a member of the Zephyr project, the technical steering committee, and myself, I'm part of the release working group, and I'm also a contributor, Zephyr contributor. Right, motivation. I have already given the motivation of this talk. So I would like to show you the blinking example. What you do in bare metal, typically, what you have, maybe you have some tools to configure your hardware. This tool produces a data file that you then use in your code to configure the peripherals to access the register directly to blink the LED. Now, how do we do that in Zephyr? It's slightly different. We configure the project to enable the GPIO subsystem. We query the Devicetree, and we then use the GPIO API to blink the LED. So again, what I want to investigate with you is the impact on code speed and size and how Zephyr handle that. The first ingredient I want to discuss with you is kconfig. So what is kconfig? Maybe the best is to see an example of kconfig. Here is an example of kconfig. As you see, first of all, that's a text file that describes the kind of configuration item you have. Here I have a config blink key, which is a Boolean options that depends on the GPIO subsystem. It means I can only have this option if the GPIO subsystem is enabled. And if this blinky option is enabled, then later on, I can set the blinky speed. And as you see here, this item have a type, like here it's an integer, we can define range, we can define default value, and so on. And as you might guess, this kconfig, that's the way we can select the different building block we want to have for our product. So kconfig is the way you can customize Zephyr for the product you are doing. Now, how do you do that? Practically, you have in your project something called project.conf. This is where you define the options and the setting you want for your product. So right now, Here, what you see is the corresponding kconfig option. Here we have this winter tour meter demo. The group of options, I cannot go there because right now the option is not enabled. And so let's enable that now. I will enable the option config blinky. And if I rebuild, now the option will be available. So now we have the option and we see that the blink frequency is set here to 10, so 1 Hertz. All right. So now is the question, okay, that's good. We have this configuration we can do with kconfig. We can describe all these options. And with project.conf, we can set up the option for a project. Now, when we call with build, when we build, what will happen in the build folder, two files will be generated, the .config file and the autoconf.h. The .config file is the summary of all options that is set and not set for your project. Whereas here, the autoconf.h has the corresponding translation to a defined macro. Now what I can do, in my project, I can use if config blinky and then have some code, and if the code is not defined, then have something else. And here, for example, we see this config blinky resolved to 10. So what happened? The build system will generate from all this configuration a corresponding header file. And this header file, you don't have to include it. It's included automatically by the build system. All right. So you can have conditional compilation. That's how you can, if certain options are enabled, extend the structure, have certain function at code level. There is another way also at build level. You can say, okay, here, if the config blinky option is enabled, then I would like to include in the build this blinky.c. So the advantage of using kconfig, as you see, it's a structured way to have all these configuration. I don't have to mess around in some header files. So now it's time to build and to see what happened when I build the project. It's quite slow because I'm running on battery. So here you see all the library that has been built. And what Zephyr does when you build your project, it will build archive. As you see here, for example, the lib kernel corresponds to the whole kernel APIs. Or here you see here the different driver that is built for this system, and so on. Now, if you look at the total sum of all this archive, we have 2 megabytes. That's not really embedded, right? And there is even something missing is the C library. Here we have picolibc. That's not the stub, but the hook. But the C library is also missing. The C library is coming from the SDK. It's 1.7 megabyte. So we have in total 3.7 megabyte. But if we look at the size of the executable, and what we flash on the target here, what you see on the left is the size in kilobyte. The corresponding image, ELF image, is 660 kilobyte, still quite big. Then the binary file that we flash on the target is 24 kilobyte. So now, how do we go from 3.7 to 24? I mean, Zephyr does that for us, okay? First of all, the transition from 660 to 24 kilobyte. Here, that's quite easy. That's a classical build post-processing step in embedded, where you just extract the portion from the L file that you need with option dump or option copy, for example. So that's classical. But here, how do we go from 3.6 to 600 kilobyte? What's the trick behind it? And the trick is a very old trick, which is coming from System 5. So it's 42 years old or something. And it has to do with the archive. When we look at the archive, so for example, here the lib kernel, you see that the archive is composed of compile unit. For example, here, the samc.obj implement all the API relative to using a semaphore. Now the point, my code is not using semaphore. And the linker is clever enough, since System 5, to see, hey, the semaphore are not used. There is no reference inside this sem.c.obj. And so the linker will remove that from the final ELF file automatically. So you don't pay the price for the things you are not using. And we can check that. Here we see in the library, kernel library, we have the function defined here for the semaphore. But if we look now in the kernel, if the same init object is there, no, that's the kernel. I wanted to look in the Zephyr file, sorry. The L file, yes. In the L file, as you see, it's not there. All right. So I think from time. Okay, the next abstraction I want to show you quickly. 26, okay. I want to show you the Devicetree. So here, typically the code for reading for the LED, you will query the Devicetree for LED 0, and then you will look at the GPIO's property, and then you can use the corresponding here GPIO pin, configure your pin to be output, and then to toggle the GPIO. So now this GPIO or this Devicetree, this is coming. This is again like kconfig describe is a domain-specific language for option. Devicetree is a domain-specific language that describes a tree-like data structure for the hardware. So for example, here we see if we want to blink this LED LED, we need to use pin 10 on port 0. And that's exactly here the information that you have here. I use port 0 of my GPIO controller, pin 10, and here I need to drive the signal to low to blink the LED. Here the Devicetree simply contains the information that we have in the reference manual and in the schematic. So when you build a project, there will be a Devicetree from the board that is coming. You can also modify this Devicetree for your project. Here you see corresponding LED 0, and here we see the red LED, the definitions. Now, and I will quickly finish with that. When we query the Devicetree here, it looks like an API, but if you, what happened, it's a macro actually. And you see it's expanded to this port, to this struct initializer here. You see pin is 10, the flag is 1, and here the port refer here to the GPIO device. So the nice thing is that the Devicetree is resolved by compile time. It's not in memory and you don't have runtime penalty. It's used to initialize data structure at compile time. So we don't have any runtime penalty in terms of speed and size. It's like an API. The bad part is when it does not work. Here you can get strange compile error. Also, you can get this device or DTS is not resolved. Here, this one means that you don't have enabled the drivers. And the ugly part is really in driver. Finally, I just want to show you when we toggle the LED, how many calls do we have? So let's do that together. Here, I toggle the LED, so I have one call. Then it call this function. Second call. Then he do some stuff. He call another third call. Then there are some stuff with the user space, fourth call. And finally here, it would be calling the GPIO. And I mean, you see 5 indirection. So it looks very dramatic. Just for toggling here this GPIO. But fortunately, all the functions are static, declared as static inline. It means it gives a good in for compiler optimization. And here you see the corresponding assembly call. There is only this instruction here in one call to this function, and here this is toggling the GPIO. So it's really efficient. And to finish, and thank you, I slightly over time, so thank you very much for your patience. We have seen techniques how Zephyr can remove the dependency to the hardware without sacrifice, without costing too much in terms of memory usage and speed. And there are really good advantage we can take of that. For example, with the native simulator that can be used to develop and test without hardware. And by just changing the device tree, if you do things right, you can port from the native simulator to the real hardware. And here I give you some example. You can also test driver. That's really great.